Have you ever wondered what it feels like to witness something that shouldn't be here at all? A traveler, cold, ancient, and utterly alone, emerging from the darkness between the stars. That's what astronomers saw when 3I Atlas appeared, a faint, distant glimmer moving just wrong enough to raise every eyebrow. You see, we've met such visitors before: Oumuamua, Borisov, each one rewriting our sense of what ordinary means. But 3I Atlas, well, it arrived with an air of uncertainty. Its orbit screams interstellar, its behavior hints at cometary, yet something about it feels off, as if the universe itself had rolled a strange die and invited us to watch where it lands. Science, after all, lives on these rare intrusions. We build models, we test them against the heavens, and when something breaks the pattern, we don't panic. We listen, because sometimes, in that noise, there's a new kind of music. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. And, where are you tonight? Are you somewhere beneath a wide, clear sky, or in a city where the stars fight to be seen? Let me know where you are in the world and what time it is where you're listening. It's always fascinating to see who's joining us from all around the world, so let's continue. You know, the phrase black swan wasn't born in the sky. It came from philosophy, from the humbling realization that for centuries Europeans believed all swans were white until someone sailed to Australia and found one that wasn't. And that moment, simple as it sounds, shattered a certainty. In science, such moments are precious. They remind us that what we think we know might only be a fragment of a much larger picture, painted in colors we haven't yet seen. When we talk about a black swan event in astronomy, we mean something rare, something that breaks the rules in a way that forces us to rewrite them. It must be improbable, impactful, and only truly understood after it has already happened. In other words, a black swan is a teacher that arrives late, and yet it leaves the deepest lessons. Perhaps you've noticed how the universe has a strange sense of timing. Just when we think our models fit perfectly, when gravity, chemistry, and light all fall neatly into place, something flickers at the edge of observation. A signal too bright, a comet too fast, a motion that doesn't quite belong. And we find ourselves wondering, not in fear, but in awe. What have we just seen? That's the beauty of science. It thrives not on certainty, but on curiosity disciplined by evidence. Every rule we hold today was once a question, and every mystery begins as a whisper in the data. The black swan, in this sense, is not chaos. It is the invitation to listen more carefully. You see, in astronomy, our expectations are built from patterns, the predictable paths of planets, the familiar light curves of variable stars, the soft comas and glowing tails of comets. These are our white swans, our well-behaved citizens of the solar family. But when something arrives that doesn't quite fit, the first challenge is to resist the human urge to overreact. Our minds are pattern-making machines. We see faces in clouds, shapes in noise, intention in randomness. So when the cosmos throws us a curveball, the real test is to look, to measure, and to wait. The first interstellar visitor we confirmed, Oumuamua, taught us that lesson with quiet elegance. Its path was too fast to be bound to the sun, its brightness flickered oddly, and it seemed to accelerate without a clear source of thrust. Many rushed to wonder if it was artificial, a fragment, perhaps, of something built elsewhere. But patient analysis suggested more earthly possibilities: jets of gas, invisible from Earth, dust reflecting unevenly, or a shard of ice behaving in ways we hadn't modeled before. It reminded us that strangeness is not the same as impossibility. Then came Borisov, the second known interstellar traveler. and it looked exactly as we'd expect a comet in every sense, shedding gas and dust as it neared the Sunday. Its arrival restored balance. It told us that visitors from other stars might be less exotic than our imaginations feared. And yet, the pattern, once set, became a benchmark. So when a new object like 3I Atlas appeared, faint and ambiguous, it reopened the door to wonder. What makes a celestial event a black swan is not only its rarity, but the way it reshapes our expectations. When we encounter something that doesn't fit into our models, we are forced to examine the architecture of our own thinking. We ask, are we missing a mechanism, a variable, a piece of the equation? Or are we witnessing a phenomenon that demands a new language altogether? In that space between knowing and not knowing, science becomes philosophy in motion. You might imagine the night sky as a calm and predictable place, but it is in fact a vast laboratory of exceptions. Every comet, every supernova, every flicker of light from a distant quasar is an experiment already running, with results written across time and distance. Our instruments merely arrive late to the reading. So when something like 3I Atlas drifts into our telescopes, we are catching the tail end of a story that began in another system, under another sun, perhaps billions of years ago. It is, quite literally, a messenger from elsewhere, carrying with it the chemistry, the dust, the frozen whispers of another world. The term beyond the parameter space is one astronomers use with a mixture of excitement and caution. It means that an observation lies outside the boundaries of what our current models predict. Too bright, too slow, too elongated, something doesn't add up. But that's where progress happens. For every equation that perfectly fits the known, there must be one that stumbles on the unknown. The universe, it seems, enjoys keeping a few surprises in reserve. Still, there's a danger in falling in love with anomalies. Humans are emotional creatures, even in the most technical of sciences. When we find something that breaks the pattern, our imagination lights up. We start building castles of explanation before we've even finished measuring the foundations. That's why the discipline of skepticism, the art of waiting for data, is so essential. Not the kind of skepticism that denies, but the kind that asks, again and again, what else could it be? In astronomy, there's a quiet humility that runs beneath the equations. We know that our instruments are limited, our sampling biased by where we happen to be in the galaxy. We know that for every comet we observe, countless others pass unseen, their stories unrecorded. So when a rare visitor like 3I Atlas enters the field of view, we are not just collecting data, we are peering into the cosmic lottery, one that has been running since before life began on Earth. Perhaps that's why the term black swan resonates so deeply in this context, because it speaks not only to the rarity of the event, but to our emotional response to it, that flicker of disbelief, followed by wonder. It's the moment when the universe reminds us that our knowledge, vast as it seems, is still a candle in an infinite night. There's a strange poetry in this, isn't there? To realize that every new discovery is both a step forward and a confession of ignorance. When astronomers label something as anomalous, they're not saying it's wrong. They're saying it's interesting, it doesn't yet fit, and therefore it's worth the long hours, the calculations, the late nights at the observatory. The anomaly becomes a compass pointing toward the next frontier. And that's the real story of 3I Atlas so far. It's not about the immediate mystery of what it is, but about what it represents, the living edge of our curiosity. Like all potential black swans, it asks us to slow down and look twice, to question how we define normal in a universe that delights in the extraordinary. In a way, a black swan event is a mirror. It reflects both the universe's unpredictability and our own limitations as observers. The comet does not change because we see it. We change because we notice. And with each such encounter, our models of the cosmos grow not only more precise, but more humble. Perhaps that's the lesson these visitors bring. The rare, the improbable, the ones that slip through the net of expectation, they remind us that science is not about having all the answers, but about being ready for the next surprise. Every unexpected curve in a comet's trajectory, every unexplained acceleration, every fragment of light that refuses to behave, these are invitations, not threats. The truth is, the universe doesn't owe us predictability. It owes us nothing at all. And yet, it offers clues freely, scattered like breadcrumbs across the darkness, waiting for us to follow. That's what makes astronomy so human. It's not only about measuring the stars, but about learning to live with uncertainty, to find meaning in patterns that might never fully resolve. So, when we talk about black swans in the sky, we are really talking about ourselves, about our capacity to be astonished, to rebuild our understanding again and again. 3i Atlas may or may not turn out to be truly exceptional. Perhaps in time, it will settle neatly into the category of natural cometary behavior, explained away by more precise data. Or perhaps it will continue to defy those explanations, nudging us toward a deeper realization of how little we know about the interstellar neighborhood. Either way, the story is only beginning. The black swan, once seen, can never be unseen. It changes not only the way we interpret the cosmos, but the way we imagine our place within it. Because in the end, the greatest discoveries are not the ones that confirm our beliefs, but the ones that gently dismantle them. And as we turn our gaze from the concept of rarity toward the long history of these interstellar wanderers, those that came before 3i Atlas, we begin to see a pattern emerge. Not of chaos, but of continuity. Each visitor, each anomaly, becomes a verse in an ongoing dialogue between our instruments and the infinite sky. And that, you see, leads us naturally to the next question, the one that begins with the first interstellar traveler we ever met. When we trace the history of our encounters with interstellar visitors, we are really tracing the story of how curiosity matures. Because before 3i Atlas, before the whispers of something strange at the edge of our instruments, there were two travelers who changed the way we see the sky. They were small, faint, and fleeting. Yet they left behind lessons that continue to echo in every new observation. The first one appeared suddenly, as if from nowhere. It was called Oumuamua, a name from the Hawaiian language, meaning a messenger from afar arriving first. And that name, well, could not have been more fitting. For generations, astronomers had speculated that fragments from other stars might one day wander through our solar system, but it was an idea tucked away in the margins of textbooks, a theoretical curiosity. Then, in the autumn of 2017, the theory became real. Oumuamua's path was unmistakable. It entered from above the plane of the planets, looped around the sun at great speed, and departed again into interstellar space. Its orbit was hyperbolic, meaning it was not bound by the sun's gravity. That was the first clue. This object did not belong here. It was a traveler from another star system. But it wasn't just its trajectory that stirred the imagination. Its light curve, the pattern of probably, its brightness as it spun suggested an elongated, cigar-like shape, or perhaps something flat and tumbling. And then there was the acceleration. It was moving just a little faster than gravity alone could explain. For a moment, it seemed the universe had dropped a riddle at our doorstep. Some called it an interstellar comet. Others whispered that it could be something artificial, a fragment, a sail, a relic from a civilization far older than ours. It was a beautiful idea, and perhaps that was why it spread so easily. But science asks for more than beauty. It asks for consistency. As data accumulated, a quieter explanation emerged. The acceleration, small though it was, could be caused by outgassing jets of volatile material sublimating from the surface, like invisible streams of vapor nudging the object along. Yet no gas was detected. That paradox remains one of astronomy's most elegant puzzles, not because it suggests aliens, but because it reminds us of how delicate our interpretations are. We saw no gas, but perhaps the emissions were faint, or the geometry of the jets kept them hidden. The surface might have been coated with a thin crust of carbon-rich material, sealing in the volatiles until sunlight fractured the layer unevenly. Outgassing without visible tails is rare, but not impossible. So the story of Oumuamua became a lesson in restraint. Extraordinary claims require extraordinary evidence, and absence of evidence is not evidence of the extraordinary. Even so, Oumuamua left a mark deeper than any photograph. It showed that interstellar objects are not myths. They exist, they travel, and some of them pass close enough for us to see. It also exposed the fragility of human perception. Faced with something we had never seen before, we reached for the language of wonder. That impulse to look beyond the known is what keeps science alive. But it must walk hand in hand with skepticism. Not long after, the cosmos sent another visitor, as if to balance the equation. In 2019, a comet named Borisov swept into the solar system. Unlike Oumuamua, Borisov looked exactly as a comet should. It sprouted a bright coma, shed gas and dust, and displayed a classic tail. Its orbit too was hyperbolic, confirming its interstellar origin, but its behavior was comfortably familiar. This was the universe's gentle reminder that not all visitors are mysterious. Some are simply distant cousins of the comets we already know. Borisov's light revealed a composition rich in cyanide and carbon monoxide chemical signatures that matched what we see in the colder regions of our own cometary family. In other words, Borisov could have been born in any number of planetary nurseries scattered throughout the galaxy. It was a fragment of another world, yes, but not a strange one. Its presence suggested that the processes shaping our solar system are not unique. Across the stars, ice, dust, and sunlight conspire in the same quiet chemistry. Spectroscopy played a crucial role in unraveling Borisov's nature. By splitting its light into a spectrum, astronomers could read its chemical fingerprint, detecting the subtle emissions of gases as they sublimated. The polarization of its light, how it scattered differently depending on the orientation of dust grains, told us about the size and texture of the particles. And the way its brightness changed with distance from the sun revealed the pace of its sublimation, the rhythm of its activity. It was, in essence, a portrait of a comet painted in physics rather than ink. Where Oumuamua had left us with questions, Borisov offered grounding. Together, they formed a dialogue, one anomaly, one confirmation. From that pairing, a pattern emerged. Interstellar visitors might not all be extraordinary. Some may be perfectly natural, but the rare ones, the outliers, will always test the limits of our models. The transition from Oumuamua to Borisov also marked a shift in the way scientists and the public perceive cosmic anomalies. With the first object, imagination ran wild. With the second, analysis reasserted itself. We learned that skepticism is not the opposite of wonder. It is the vessel that carries wonder safely through uncertainty. And now, with 3i Atlas moving slowly through our telescopes, we stand at a new threshold. Its faint signature recalls the early days of both Oumuamua and Borisov, ambiguous, fragile, alive with potential. We know enough now to ask better questions. What are we really seeing when a small body from another system crosses our sky? How much can we infer from the patterns of light alone? What do its brightness, its coma, its tail, its color temperature tell us about the chemistry of distant suns? If you think of each interstellar object as a letter, then 3i Atlas may be the third line in an unfolding message. The first line, written by Oumuamua, whispered uncertainty. The second, by Borisov, offered reassurance. The third may speak of synthesis, a new understanding that blends the two. To read it, we must continue refining our instruments, comparing spectral data, and mapping light curves against every known model of cometary behavior. And perhaps, in time, we'll begin to see a broader story. These travelers, fleeting and faint, are not isolated wonders. They are samples, physical links to other star systems, drifting between gravitational wells like spores on a cosmic wind. They carry within them the fingerprints of their birthplaces, the balance of volatiles, the pattern of irradiation, the scars of collisions, the quiet testimony of billions of years. Each one is a fragment of a history written far away. There's something almost poetic in that realization. When we study them, we are not only measuring rock and ice, we are touching, however briefly, the geology of another sun. The idea that our solar system is open, porous, a crossroads of galactic debris, that is a humbling thought. It means the boundaries we draw in space are illusions. The cosmos mingles freely, exchanging fragments like conversations between distant neighbors. And in this mingling, there is continuity. The lessons of Oumuamua and Borisov help us anchor our expectations, so that when something new appears, something that might behave just slightly differently, we have a framework. We no longer rush to the extraordinary explanation. We begin, instead, with the ordinary laws of physics, stretched and tested at the edges. Still, you can feel it, can't you? That pulse of possibility when the data doesn't quite fit. We stand on the bridge between certainty and speculation, and in that space, imagination and measurement meet. 3i Atlas may follow the same path as Borisov, confirming that most interstellar visitors are simply comets on long journeys, or it may deviate, just enough to make us wonder again. You see, that's the rhythm of science oscillating between discovery and doubt. Each new object resets the balance. We learn, we adapt, and then the universe surprises us once more. It's a conversation that never ends. The light we capture from these travelers, faint as it is, contains more than data. It contains stories of formation, of migration, of survival. And when we decode that light, we are, in a way, listening to other solar systems breathe. The story of interstellar visitors is not about singular events, but about a lineage of understanding. From Oumuamua's enigma to Borisov's familiarity, and now to 3i Atlas's quiet ambiguity, we are learning how to read the grammar of the cosmos itself. Each case refines the vocabulary of our inquiry. Each anomaly teaches us humility, and as we follow the thread of this lineage, one realization grows ever clearer. To understand these wanderers, we must understand the very physics that shapes comets, the way ice turns to gas, the way dust is carried by light, the way a frozen nucleus becomes a living, breathing body under the warmth of the Sunday. It is there, in the physics of sublimation and motion, that the next chapter of this story truly begins. To understand these interstellar travelers, we must first return to the foundation, to the quiet, intricate physics of comets themselves. Because long before they became omens or mysteries or black swans, comets were laboratories in miniature, carrying within them the frozen chemistry of the early solar system. They are time capsules, fragments left untouched since the dawn of planetary formation, and yet, when they wake under the light of the sun, they become alive in the most literal sense. They breathe. You see, every comet begins as a nucleus, a small, irregular body made of dust, rock, and volatile ices. When it drifts through the cold regions of space, far from any star, it remains dormant, a frozen seed in an endless winter. But as it approaches a source of heat, something extraordinary happens. The ices begin to sublimate, turning directly from solid to gas. This is the breath of a comet, and it is what gives rise to its luminous features, the coma, the tails, the faint veils of light that have fascinated observers for centuries. Water ice, the most familiar of volatiles, becomes active when the comet is relatively close to the Sun, around 3 astronomical units or less. At those distances, sunlight is strong enough to warm the surface above the threshold where molecules escape into space. The gas carries dust particles with it, creating the fuzzy halo we see through telescopes. This coma, glowing softly in reflected light, is both beautiful and deceptive. It hides the nucleus, making direct observation difficult, and so astronomers must infer the comet's core properties indirectly from the patterns of its brightness, from the way it sheds light across wavelengths. But not all comets follow the same rules. Some awaken much farther out, at 5 or even 10 astronomical units, where water remains frozen solid. In those cases, other ices, carbon dioxide, carbon monoxide, methane, or ammonia take the lead. They are more volatile, more eager to sublimate, and they can drive activity in regions where sunlight is weak. When we see a comet brightening unexpectedly at great distance, it is often because these exotic ices are stirring beneath the surface, venting through cracks like steam from the crust of an ancient world. This balance between water and carbon compounds is not random. It encodes the conditions of the comet's birth. Bodies formed farther from the Sun, in the frigid outskirts of the protoplanetary disk, preserve more carbon monoxide and carbon dioxide. Those that condense closer in are richer in water and poorer in volatiles. So, by measuring the composition of a comet's gas, we can trace its origin not just where it is now, but where it once belonged in the great nursery of planets. As the gases escape, they carry dust grains outward, sculpted by the gentle pressure of sunlight and the push of the solar wind. Over time, this interplay produces the comet's twin tails. One, composed of neutral dust, curves gracefully along its orbit, shining in reflected sunlight. The other, made of ionized gas, streams directly away from the Sun, drawn taut by the solar magnetic field. Together, they form a kind of cosmic compass, marking both the path and the direction of energy flow. Every tail, every shimmering plume, is a map of physics in action. The dust tail responds to radiation pressure, the constant push of photons imparting momentum. The ion tail responds to electromagnetic forces, the charged particles of the solar wind sweeping ions into long, straight filaments. When you see a photograph of a comet stretching across the sky, you are looking at a dynamic equilibrium, a balance between heat, light, and motion, between chaos and order. And yet, the most subtle force at play is the one least visible. As gas vents from the surface, it imparts a small but measurable thrust. The comet, in effect, becomes its own engine. This non-gravitational acceleration can slightly alter its orbit, causing it to deviate from the purely gravitational path predicted by celestial mechanics. Over many weeks or months, those tiny jets can add up, shifting the comet's trajectory enough to be noticed from Earth. For ordinary comets, these deviations are expected. We model them, we calculate the coefficients that describe their outgassing patterns, and we adjust the orbit accordingly. But for interstellar objects like Oumuamua or 3I Atlas, where the physical structure and rotation are unknown, such accelerations become deeply intriguing. They are fingerprints of activity, subtle hints that beneath the surface, something volatile is stirring. Imagine standing on the surface of a comet, if such a thing were possible. The horizon curves sharply. The ground beneath your feet is black and porous, made of ancient dust fused with ice. As the sun rises, the temperature climbs, and tiny geysers of vapor begin to erupt, invisible jets shooting into space. Each puff is small, perhaps only a few grams of gas per second, but there are thousands of them. Over time, they reshape the nucleus, carving pits and grooves, spinning it faster. If the jets are asymmetric, the entire body may begin to tumble, its rotation irregular, its motion unpredictable. That's the hidden drama behind every comet's tranquil glow. What we see from Earth, the luminous halo, the flowing tails, is merely the outer performance. The real story is one of physics working quietly at the microscopic level, of sunlight unbinding molecules that have slept for billions of years. In studying these processes, astronomers rely on light curves, on the way brightness evolves with distance from the sunday. For most comets, luminosity follows a power law, a predictable relation that depends on how rapidly sublimation increases as solar heating intensifies. Deviations from that curve tell us something is unusual. Perhaps the surface is coated with insulating dust, delaying the outburst. Or perhaps deep fractures are venting gases unexpectedly, releasing energy from within. The interplay between heat and material is delicate. A comet's surface can change dramatically during a single passage. Dust may settle, new layers may form, and internal voids may collapse. In some cases, rotation accelerates to the point of instability, leading to fragmentation. Others remain remarkably stable, enduring many cycles of approach and retreat. Each one is a living experiment in thermodynamics, constantly adjusting to the balance of radiation and gravity. When we apply this knowledge to interstellar comets, the questions multiply. What happens to an icy body that has drifted through deep space for eons, exposed to cosmic rays, stripped of its more volatile layers? Does it still behave like the comets we know, or does it awaken in stranger ways? The faint, non-gravitational accelerations we detect could be the size of long-frozen gases finally breaking free. Or they might hint at entirely different surface physics, exotic ices, porous materials, or unusual thermal properties. That is why understanding the basics, sublimation, jets, tails, and brightness is so essential. It gives us a foundation on which to interpret the unfamiliar. When we observe a dim, distant traveler like 3i Atlas, we can compare its behavior to this template, searching for both resemblance and deviation. If it brightens too early, perhaps carbon monoxide is driving the activity. If its acceleration is weaker than expected, perhaps its jets are balanced symmetrically, cancelling out their effects. The dance of cause and effect continues, subtle but decipherable. You know, it's easy to forget that comets are not static relics, but dynamic systems. They respond instantly to their environment, and that responsiveness is what makes them so rich with information. They are thermometers, barometers, and recorders all at once. Through them, we can watch the conversation between sunlight and matter unfold in real time. What fascinates me most is how these tiny bodies, often no more than a few kilometers wide, can reveal such vast truths. In their chemistry, we glimpse the conditions of planetary formation. In their motion, we measure the precision of gravity. In their light, we see the unity of physics, from the smallest dust grain to the great galactic structures. And so, as we turn our gaze back to 3i Atlas, equipped with this understanding of cometary mechanics, we find ourselves better prepared to listen. We can now interpret its faint glows and silent accelerations not as mysteries, but as voices in a familiar language. The challenge, as always, is to distinguish what is truly new from what is simply misunderstood, because sometimes what looks like a black swan is merely a white swan in unfamiliar light. But sometimes it is not. The distinction lies in detail in the spectrum, the geometry, the rhythm of motion. And to uncover those details, we must go deeper still, into the mathematics of the orbit itself, into the geometry of interstellar motion. For the path a comet follows tells us as much about its nature as its chemistry does, its inclination, its eccentricity, the shape of its approach. These are the lines of the story it writes across space. And so, from the physics of the comet's breath, we move naturally to the architecture of its journey, to the great arcs and curves that bind or free it from the pull of the Sunday. The journey of a comet is not a random path across the sky. It is geometry written in motion, a slow dance choreographed by gravity itself. Every curve, every deflection, every faint shimmer of its trail follows rules as old as the universe, yet each case carries its own delicate nuance. To understand the orbit of something like 3I Atlas, we must imagine the space it moves through, not as empty, but as a grand stage where the forces of the Sun, the planets, and interstellar momentum meet. When an object travels from another star system, it enters ours at a speed too great to be captured by the Sun's gravity. Its trajectory is not an ellipse, like the gentle, repeating loops of planets and long-period comets. Instead, it takes the shape of a hyperbola, an open curve that never closes. The mathematical signature of this shape is its eccentricity, a number greater than 1. The larger that number, the more open the orbit, the more clearly interstellar its origin becomes. For a moment, imagine watching the solar system from above. The planets form a thin disk, orbiting neatly along the ecliptic plane, like pearls strung on an invisible thread. Now picture an intruder, an icy fragment crossing this flat world at an angle, diving in from above, slicing through the disk, and then vanishing into the depths below. That is what a hyperbolic trajectory looks like, an arc that cuts across the well-ordered geometry of the planets. These orbits are not arbitrary. The inclination, the tilt of the path relative to the ecliptic, tells us how alien the object's motion truly is. A shallow inclination means it skims the plane of the planets, perhaps sharing some ancestral alignment with the solar system. A steep inclination, even a retrograde one, means it comes from an entirely different direction, a messenger from a region unconnected to our own. Some comets move prograde, flowing with the planets around the Sunday. Others, like rebels, move retrograde, against the stream. That reversal of motion is not just a curiosity. It tells us about the angular momentum of their journey through interstellar space. The Sun's pull bends these paths inward, a gentle curvature that reveals much about both the speed and the origin of the traveler. As 3I Atlas entered the solar system, its velocity relative to the Sun placed it far beyond the reach of any gravitational capture. It would come close, sweep through, and then depart, forever carrying the trace of our star's influence in the bend of its trajectory. The precise shape of that curve, measured by observatories around the world, allows astronomers to reconstruct its entire history, where it came from and where it will go once it leaves. There is something poetic about that. The orbit of a comet is a story written backward. We see only a few pages as it crosses our field of view, yet from those fragments we infer an entire journey that began perhaps in the gravity well of another star, ejected by some ancient disturbance, a collision, a close encounter, a stellar wind strong enough to fling it into the dark. And now, for a few short months, it shares our sky before fading again into the endless cold. When astronomers describe such motion, they use not only mathematics but imagery. They imagine the Sun at the center of a vast coordinate grid, the planets circling like dancers on concentric tracks. Then, from a distant corner, a faint line cuts inward. The incoming branch of the hyperbola swings by the Sun at its closest approach, known as perihelion, and then sweeps outward again, mirrored and reversed. That closest point, perihelion, is the heartbeat of a comet's orbit. It determines how bright it will appear, how active it may become, and whether we will ever have the chance to study it in detail. For 3I Atlas, this moment of closest approach defines the window of opportunity. Before perihelion, the comet brightens slowly as sunlight warms its surface. Afterward, it fades, its activity waning as it retreats into the cold. But the geometry of the orbit, its angle, Its tilt, its alignment with Earth's position, decides how much of that process we can actually see. If the comet passes behind the Sun, from our perspective, it may be invisible at its most active. If the comet orbit aligns favorably, it can be followed from both northern and southern hemispheres, offering a rare full portrait. The phase angle, too, matters deeply. That is the angle between the Sun, the comet, and the Earth, a measure of how we view the illuminated portion of the comet's coma and tail. At small phase angles, we see the comet more fully lit, its brightness near maximum. At larger angles, it becomes backlit, the dust and gas glowing faintly as sunlight filters through. These subtleties shape the data we collect, the spectra we interpret, and the models we build of its surface and activity. Perhaps the most challenging part of studying such an orbit is its transience. Unlike periodic comets, which return predictably every few decades or centuries, an interstellar object like 3I Atlas gives us only one pass. There is no second chance. The geometry of its motion dictates not only how we see it, but also how much we can learn before it fades forever. Observatories must coordinate globally, timing their observations as the comet sweeps through the inner solar system. Each image, each spectrum, becomes part of a fleeting archive of a traveler that will never return. You might wonder why the shape of an orbit holds such emotional weight for scientists. It's because orbits are more than lines, they are records of encounter. The hyperbolic path is a signature of escape, the mathematical form of freedom. To study such a trajectory is to glimpse a moment of interaction between our Sun and something vast beyond it. For a few days or weeks, gravity ties the two together in a silent conversation, then releases them once more to their separate destinies. And that, you see, is why orbital geometry is more than just mathematics. It is the language of cosmic relationships. When we chart the motion of 3I Atlas, we are not merely plotting numbers, we are mapping the subtle dialogue between the interstellar and the solar, between the visitor and the host. Every parameter, eccentricity, inclination, perihelion distance is a phrase in that dialogue, a measure of how deeply the two worlds touch before parting ways. For the public, these concepts can be abstract, so astronomers often turn to visual storytelling. Imagine drawing the ecliptic plane as a smooth circle, the orbits of Earth and Mars tracing thin ellipses around the Sunday. Then, from a distant corner, a slanted line cuts across, dipping into the plane before rising again. A small arrow marks the point of perihelion, where the object glows brightest, and a dashed line extends outward, showing its path into the void. That single sketch captures everything: the motion, the timing, the rarity of the encounter. It is the geometry of transience rendered visible. As we refine our models, the uncertainty narrows. Radar and optical tracking improve the accuracy of the orbit, revealing subtle deviations. These, in turn, can point to outgassing, to internal processes that shift the path ever so slightly. Thus, geometry meets chemistry, once more the physical and the dynamical intertwining. And from that union, a deeper truth emerges. The orbit of a comet is not a static thing. It evolves under the influence of its own activity, reshaped by the very forces that bring it to life. It's a humbling realization. Even in the vast stillness of interstellar space, motion and change persist. The path of a comet is not predetermined. It is written as it unfolds, influenced by every jet of gas, every grain of dust, every subtle whisper of sunlight. When we plot those paths, we are not only predicting where the comet will be, we are listening to how it responds to the universe around it. And so, as we trace 3I Atlas through its hyperbolic journey, we find ourselves standing at the threshold between mechanics and story. The equations describe the shape, but the meaning lies in the interaction, the brief communion between an interstellar traveler and our local star. It's path through the solar system is a single brushstroke on a cosmic canvas, connecting two realms for a fleeting moment before parting forever. But to truly understand what that path tells us, we must go deeper still. We must look not only at how it moves, but at what it's made of, because the orbit is the outer geometry of a story whose inner chapters are written in chemistry. The way it glows, the gases it releases, the ratios of water to carbon dioxide to carbon monoxide, these reveal where it was born and what it has endured. And so, from the language of motion, we turn to the language of matter itself, to the cold chemistry that awakens under sunlight and tells us how even the most distant visitor carries the memory of its origin. When we look at a comet like 3I Atlas and call its data strange, what we often mean is that it resists our first expectations. The brightness may fluctuate in ways that seem inconsistent, or the measured acceleration might not match our neat equations. But, you see, strangeness in science is often a mirror reflecting not something supernatural, but the limits of what we know. It reminds us that the universe is never obligated to behave according to the tidy lines we draw for it. And so, before we rush to imagine something extraordinary, we must first learn to question our own assumptions. The first and most fundamental principle in that approach is this: natural phenomena can appear strange simply because they are complex. Take, for instance, the subtle accelerations we sometimes observe in comets. When the outgassing jets are distributed unevenly across the surface, the tiny forces they produce do not add up neatly. One jet may push in one direction, another may counter it, and together they create what looks like a random wobble. To an observer on Earth, that irregularity can resemble an external influence or an unexplained perturbation. Yet it is simply the product of internal balance to a comet's own breath, steering its path in unpredictable ways. Now imagine if those jets are not only uneven but also vary with the comet's rotation. As it spins, sunlight strikes different regions, activating new vents while extinguishing others. The result is a dynamic pattern of thrust that shifts over hours or days. From our perspective, the comet's acceleration seems inconsistent, even mysterious, but it is in fact perfectly physical, a tiny, ever-changing dialogue between sunlight and ice. Sometimes, the outgassing can be almost symmetrical. Jets firing in opposite directions cancel each other out, reducing the net acceleration to near zero. That might make the object appear inert, when in truth, its surface could be furiously active. The geometry of the vents, the spin rate, the distribution of material, all these details conspire to shape the forces at play. Without knowing them precisely, our models will always carry a margin of uncertainty, a gap where speculation easily slips in. Dust plays a part as well. Many comets release particles larger than we expect, grains that move sluggishly under the influence of light pressure. These heavy grains remain close to the nucleus, altering the way brightness changes over time. When we see a slow fade, where a rapid one is predicted, or when the coma remains extended longer than expected, it can tempt us to believe something unusual is happening. But often, the answer lies in the physics of grain size and reflectivity. Larger particles scatter light differently, and they are more resistant to the sun's radiation. What seems wrong can therefore be quite natural, hidden in the subtleties of material behavior. Another layer of uncertainty comes from the size and reflectivity of the nucleus itself. Comets are faint, and we rarely observe their solid cores directly. Instead, we estimate their size by comparing how much light they reflect with how bright they appear. But albedo, the measure of reflectivity, can vary widely. A dark surface reflects little light, making the nucleus appear smaller than it really is. A brighter surface does the opposite. If we misjudge that value, our inferred size can be off by a factor of several times. And once that happens, every related calculation, mass, density, thrust from outgassing, inherits the same uncertainty. What looks like an anomaly may just be an artifact of assumption. Science, when done well, embraces such uncertainty. The unknown is not a flaw. It is the reason we observe, the reason we measure again and again. But in the age of instant communication and speculation, there is pressure to explain too soon. A single data set can inspire headlines that leap far beyond the evidence. The lesson of both Oumuamua and Borisov, and now 3i Atlas, is that patience remains the truest scientific virtue. Before we invoke the extraordinary, we must exhaust the ordinary in all its hidden complexity. Think of a comet's activity like the breathing of a living thing. It is irregular, responsive, sometimes calm, sometimes eruptive. A burst of gas might appear one day and vanish the next. Surface fractures open and close, exposing or concealing volatile ices. These micro-events can mimic non-gravitational forces, altering trajectories just enough to confuse our models. The apparent mystery is born not from physics failing, but from our limited vantage point. We are watching a symphony through a keyhole, hearing only fragments of its true melody. There's also a danger in the way human cognition handles anomalies. We are pattern-seeking creatures. When something deviates from expectation, we instinctively look for meaning, and sometimes we find patterns where none exist. A random distribution of light fluctuations may appear to follow a rhythm. A coincidence in timing can be mistaken for causation. It takes discipline to recognize when our minds are filling gaps with imagination rather than data. This is why astronomers rely so heavily on models not as prisons of thought, but as anchors against the tide of intuition. The correct approach is not to deny anomalies, but to stress test them. When the data do not fit, we build models rich in parameters and explore their limits. We simulate different rotation periods, surface compositions, and jet configurations to see how they affect the observed motion. In doing so, we find that what initially looked like something impossible often falls comfortably within the range of the natural. Each test strips away a layer of mystery, leaving behind a clearer picture. It is tempting, of course, to jump to the extraordinary explanation. The idea that a comet's odd acceleration might signal alien technology, or that its brightness changes could reveal an artificial design, is captivating. It awakens something primal, the hope that we are not alone. But that hope, however beautiful, cannot substitute for evidence. The universe is wondrous enough without our embellishments. To respect that wonder fully, we must first be rigorous in how we interpret it. The story of 3i Atlas, in many ways, is a story about restraint. As it drifts through the solar system, every new observation brings whispers of anomaly, its faint brightness, its ambiguous activity, its uncertain acceleration. Yet each of those whispers must pass through the filter of physics. Are the jets balanced? Is the surface more reflective than we assumed? Is the dust grain distribution skewed toward larger particles? Each question narrows the possibilities, pulling the extraordinary back toward the comprehensible. In this way, skepticism becomes a kind of reverence. It is not cynicism. It is the patience to let the data speak in its own time. When scientists challenge their own interpretations, they are not suppressing wonder, they are protecting it. Because when the evidence finally does point beyond what we know, it will stand on solid ground. It will shine all the brighter for having survived the crucible of doubt. And perhaps this is the deeper meaning behind the idea of the black swan in astronomy. It is not about chasing the miraculous, but about understanding the rare in a disciplined way. A black swan event is only meaningful because it rises from a sea of ordinary observations that we trust. To recognize the truly exceptional, we we must first understand the full range of the natural. Consider how even the smallest mismeasurement can cascade into large misunderstanding. If the assumed rotation period of a comet is wrong by just a few hours, the direction of the jets relative to sunlight changes, altering the predicted acceleration by measurable amounts. If the dust reflectivity varies with angle, the brightness curve may appear to fluctuate for reasons entirely geometric. These are the quiet lessons of precision, how every assumption carries weight, and how humility in modeling becomes an act of respect for the truth. The process of refinement never ends. Each new observation updates the parameters. Each simulation adds another layer of nuance. The models grow richer, not because we complicate them for their own sake, but because nature itself is complex. When we test and retest the old explanations, we build a framework strong enough to hold even the most unusual data. That is how science survives its own surprises, by weaving doubt into its fabric. And yet, amid all this caution, one must not lose the sense of awe. To study comets is to study impermanence, to watch ancient ices turn to vapor and vanish into sunlight. Their fragility is their lesson. Even the strange, the irregular, the apparently inexplicable, these are expressions of the same universal laws that shape everything else. When we finally see that connection, the mystery deepens rather than dissolves. So when we say that the data of 3i Atlas may be strange but still natural, we are not diminishing the wonder. We are grounding it, giving it context within the vast continuum of cosmic behavior. The comet's faint deviations, its subtle accelerations, its uneven glow, all are part of a language written in physics, waiting to be fully translated. And as we move forward, this understanding leads us toward a broader realization. For even small forces, those faint whispers of gas and dust that we once dismissed as negligible, can alter trajectories over long timescales. They accumulate, reshaping paths, setting off chains of interaction across the solar system. In that recognition lies the bridge to the next part of the story, where dynamics themselves become the focus. The tiniest perturbation, when given enough time, can ripple outward like a domino falling in slow motion, rewriting the geometry of space and the history of motion itself. When we begin to think of motion in the solar system, it's tempting to imagine everything as fixed, like an elegant clockwork turning on an unchanging axis. But in truth, the cosmos is not a clock. It is a fluid system of immense sensitivity, where even the faintest forces ripple outward through time, bending trajectories and altering destinies. The dance of planets, asteroids, and comets is not mechanical but dynamic, alive with feedback, resonance, and chaos. And that, perhaps, is one of the universe's most humbling lessons, that small things matter, and that even whispers of force can move worlds, given patience. The non-gravitational accelerations we spoke of before, those delicate jets of gas or minute asymmetries in a comet's rotation, might seem trivial on a human timescale. They are measured in millimeters per second, far beneath the threshold of our senses. But when integrated over months, years, and decades, they shift orbits enough to change the future. A comet that might have missed a planet by thousands of kilometers could, a few orbits later, swing close enough to break apart or collide. These are the domino effects of celestial press-of time mechanics, where the smallest perturbation becomes the seed of transformation. The solar system, you see, is not a stable clock. It is a sea of gravitational tides. Each planet exerts its influence, tugging slightly on everything else. Jupiter, enormous and distant, shapes the motions of asteroids, as though conducting a slow, silent orchestra. Saturn adds subtle harmonics. Even Earth and Mars leave their fingerprints, shifting the trajectories of small bodies in ways that compound over centuries. And beyond them all, the faint, collective tug of the galaxy itself stretches and folds the outer boundaries of our system. It's in this complex network of pulls and resonances that comets like 3I Atlas make their brief appearance. As it enters the gravitational field of the Sun, it passes through zones of influence regions where planetary forces overlap, creating corridors of stability and instability. In these regions, a comet's path can be deflected ever so slightly, setting off a cascade of changes. Sometimes these changes are negligible. Other times, they accumulate, turning near misses into encounters and encounters into impacts. This is why astronomers track such objects with such care. A comet's trajectory, even one that seems to escape on a hyperbolic path, is never truly free of influence. Jupiter's gravity, in particular, acts like a gatekeeper. Many long-period comets that enter from the Oort cloud are captured or ejected by Jupiter's massive presence. Some are drawn inward and fragmented by the Sun, while others are flung back into interstellar space. The boundary between these fates is razor-thin, a difference of fractions of a degree, of a few meters per second in velocity. When scientists model these interactions, they must treat the solar system as a multi-body problem, one of the most complex puzzles in classical physics. There is no closed solution, no neat equation that predicts everything. Instead, we simulate it millions of calculations per step, integrating the effects of every gravitational player. What we see, emerging from this sea of computation, is a delicate balance between order and chaos. The planets trace nearly stable paths, locked in resonances that have held for billions of years. But the small bodies, the asteroids, the comets, the fragments, live at the edge of that balance. A single encounter, a passing nudge, can change their futures forever. There is a term for this sensitivity, the butterfly effect. But in astronomy, it is more apt to think of it as the cometary effect, the idea that one plume of vapor, one outgassing event, might set a new course for an entire worldlet. When we extend these effects over cosmic time, they become profound. The architecture of the solar system itself, the placement of asteroid belts and resonance gaps, the distribution of near-Earth objects, all of it is sculpted by cumulative perturbations. The universe is a patient sculptor. You might wonder, then, whether 3I Atlas with its fleeting visit can meaningfully alter anything. On the surface, the answer seems no. It is too small, too fast, too brief a guest to leave a lasting mark. But the story is not so simple. As it passes, it interacts, not only gravitationally, but also through the dust and ion trails it sheds. Those microscopic particles spread across interplanetary space, joining the vast cloud of interstellar material that the planets continually move through. Over geological time, even such tiny deposits add to the subtle redistribution of mass and energy in the solar system. Moreover, studying such motion helps us understand our own planet's environment. Near-Earth asteroids and comets occupy dynamic corridors, regions of orbital space constantly reshaped by Jupiter's gravity and the minute effects of sunlight, such as the Yarkovsky effect, which can slowly push small bodies onto new paths. The same physics that governs an interstellar visitor also governs the rocks that one day might cross Earth's orbit. To follow 3I Atlas, then, is to practice the art of foresight, learning how to read the future behavior of the sky's debris. Resonances lie at the heart of this art. A resonance occurs when two bodies' orbital periods form a simple ratio, say, one orbit of a comet for every two of Jupiter's. In such cases, the gravitational nudges repeat in rhythm, amplifying each other over time. Like a steady push on a swing, the effect builds. Some resonances stabilize orbits, holding asteroids safely in repeating paths known as Trojan clusters. Others destabilize, creating gaps like the Kirkwood zones in the asteroid belt. These resonances are not accidents, they are the fingerprints of long-term dynamical evolution. They show us how order and chaos coexist, braided together through the quiet arithmetic of gravity. Imagine, for a moment, the path of 3I Atlas as it sweeps through the solar system. It enters from a direction tilted steeply to the ecliptic, cuts through the planetary plane, and exits toward the stars. As it passes, it crosses invisible zones of influence, the resonant harmonies of Jupiter, Saturn, and the inner planets. Each crossing imparts an infinitesimal shift, nothing dramatic, nothing sudden, but real nonetheless. Multiply that by millions of years and millions of objects, and you begin to see how the solar system reshapes itself from within. Not in cataclysms, but in quiet, persistent adjustments. This understanding transforms how we think about stability. Stability is not stillness. It is a state maintained through continuous motion. The planets keep their places not because they are fixed, but because their mutual perturbations balance out. It is a self-correcting dance, one that has persisted since the dawn of the Sunday. And in this great choreography, every comet, every asteroid, every wandering speck plays a role no matter how brief its part. For the astronomer, this awareness brings both awe and humility. To predict the motion of a comet precisely is to wrestle with chaos itself. We can project its path a few centuries ahead, perhaps a few millennia, but beyond that, the uncertainties grow exponentially. The solar system, vast as it is, carries the seed of unpredictability. It is not that physics fails. Rather, the system is too sensitive, too beautifully interwoven, for perfect foresight. And that imperfection, well, it is what gives the cosmos its character. The dynamics of these interactions also have a practical side. By tracking the subtle shifts in orbital parameters, astronomers refine their models of planetary mass distributions, testing the precision of our gravitational maps. Tiny discrepancies reveal much the unseen influence of small moons, the collective mass of asteroid clusters, even the solar radiation pressure acting on cometary dust. Thus, each interstellar visitor becomes a probe, a natural experiment in celestial mechanics. Over long durations, these cumulative forces shape the architecture of the solar system's small body population. Asteroids trapped in Jupiter's Trojan points form stable islands of matter, while others, perturbed by resonances, drift toward Earth-crossing orbits. Comets from the Oort cloud are nudged inward by distant stars and galactic tides, becoming occasional visitors. And among them, perhaps once in a generation, one arrives from beyond a true interstellar traveler like 3I Atlas, offering us a glimpse of the processes that play out in planetary systems far from our own. It is astonishing, really, how little is needed to alter the grand design. A fraction of a degree, a fraction of a second, and the path of a comet diverges into a new future. We are reminded that chaos does not mean disorder, but sensitivity, a universe so finely tuned that even the smallest actions echo endlessly. As we contemplate this interconnected motion, we begin to see how fragile, and yet how resilient the cosmic balance truly is. The forces that shape comets also shape worlds. The slow gravitational breathing of the solar system governs tides, climates, and perhaps even the conditions for life itself. To understand these interactions is to understand the subtle architecture of existence. And so, when we turn our attention back to the fragile traveler 3I Atlas, we can see its passage not as an isolated event, but as a thread woven through this grand tapestry of motion. It belongs to a lineage of movements that stretch from the birth of the sun to the edge of the galaxy. Its path, though fleeting, contributes to the ongoing conversation of gravity and time. But gravity, for all its reach, is not the only sculptor at work. Beyond dynamics lies another kind of transformation, one not driven by motion, but by fragility itself. For comets, in their dance through the heat of the inner solar system, often face an even more intimate fate. They fracture, they fragment, they shed their skins in luminous outbursts. And these breakings, though destructive, are part of the cycle too. So perhaps the next step in our journey should lead us there, to the quiet but dramatic art of disintegration, and to what those fragments can teach us about the life and death of these ancient travelers. There comes a point in every comet's life when gravity, heat, and time conspire to test its integrity. No matter how ancient or distant its origin, a comet is a fragile thing, a porous mixture of dust, ice, and voids, held together by the gentlest of bonds. It is not a solid stone traveling through space, but a body stitched together by frost and memory. As it swings close to the sun, this quiet structure begins to tremble, and sometimes, under that growing tension, it breaks. To understand why comets fragment, we must think not in terms of violence, but of accumulation. The forces that tear them apart are not sudden, but patient. They begin deep within, where sunlight penetrates unevenly, creating gradients of heat. Some regions expand faster than others, building internal stress. As volatiles sublimate, they leave behind voids, hollowing out chambers that weaken the structure from within. A nucleus that was once compact becomes a lattice of cavities and fragile bridges. Under rotation, these weaknesses become fault lines, and one day, without fanfare, a crack forms that widens into a split, dividing a comet into pieces that drift away like seeds caught in a stellar wind. One of the most well-known examples of this process is Shoemaker-Levy 9, the comet that met its fate at Jupiter in the mid-90s. Captured temporarily by the giant planet's gravity, it was torn into more than 20 fragments before plunging into the Jovian atmosphere. The images of that event remain among the most dramatic in all of astronomy, plumes rising thousands of kilometers high, scars spreading across the planet's clouds like cosmic bruises. It was destruction, yes, but also revelation. For the first time, humanity witnessed the direct collision of two celestial bodies, an event that turned abstraction into spectacle. Shoemaker-Levy 9's fragmentation was caused by tidal forces. As the comet passed within Jupiter's Roche limit, the difference in gravitational pull between its near and far sides exceeded the structural strength of the nucleus. The comet was literally pulled apart by gravity's uneven embrace. This kind of breakup is a reminder that no matter how distant or small a comet may seem, it lives in constant dialogue with larger bodies, a dialogue written in tension and release. But fragmentation is not always so dramatic. Sometimes it happens silently, without an external cause. The comet 73P Schwarzmann-Wachmann 3 is a haunting example. Over several returns to the inner solar system, it began to split repeatedly. What had once been a single nucleus became dozens of smaller fragments, each following a slightly different path. From Earth, telescopes captured images of this slow disintegration, not an explosion, but a quiet unraveling. Scientists believe that internal stress, rotation, and the buildup of gas pressure beneath sealed crusts may have driven the process. Like ice fracturing under spring thaw, the comet simply came apart under its own imperceptible strain. In both cases, the lesson is clear. Fragmentation is a natural part of a comet's evolution. It is not an anomaly but an expected stage in the life of a body made of volatile ice. The Sun is both a giver and a destroyer, awakening comets from their long dormancy even as it unravels their structure. When a comet approaches perihelion, the intense heating penetrates deeper with each passage, exhausting layers of volatiles and leaving a more brittle residue behind. The surface may appear calm, but inside, the stresses mount thermal, mechanical, rotational. Eventually, something gives. And this brings us back to comets like 3I Atlas. Interstellar travelers are older and likely more fragile than their solar cousins. They have wandered for eons through the cold emptiness between stars, their surfaces battered by cosmic rays and micrometeoroids. The volatile ices within them may have been locked for billions of years, preserved beneath insulating layers of dust. When such a body is suddenly exposed to the warmth of the sun, the awakening can be violent. Gases trapped for ages surge outward, carving fissures, spinning the nucleus faster, pushing it to the edge of cohesion. Fragmentation becomes not just likely, but almost inevitable. Astronomers recognize several telltale signs when this happens. The first is a sudden increase in brightness. The comet flares unexpectedly as new surfaces are exposed, releasing fresh material into space. Then the coma changes, becoming asymmetric or uneven. Dust jets shift direction. Polarization patterns, the way light scatters off the particles, alter subtly, hinting at new textures or sizes in the dust. Finally, multiple nuclei may appear, tiny points of light drifting apart within the halo. Each fragment carries a piece of the original, still active, still breathing, but on its own trajectory. From a scientific perspective, such events are goldmines of information. They reveal the internal structure of the comet, whether it is a single, cohesive block or a loose aggregate of clumps held by weak gravity. They show how rotation interacts with stress and how the composition of ices affects mechanical strength. Even the pattern of the fragments can tell us about the timing and cause of the breakup. Was it thermal stress? Gas pressure? A rotational spin-up? Each scenario leaves its own fingerprint. There is a kind of paradox in this fragility. To understand comets fully, we must often wait for them to break. Their destruction is our revelation. Through their disintegration, they lay bare what was once hidden, the stratified layers of dust and ice, the composition of grains, the chemical signatures of their birthplaces. In death, they teach us about the conditions of early solar systems and perhaps of others beyond our own. And yet, even as they fall apart, they remain beautiful. The fragments continue to reflect sunlight, forming new tails and comas. For weeks or months, they trace parallel paths, glowing softly before fading into darkness. It is as if the universe itself performs an elegy in light, a slow, silent farewell to something that has existed since the dawn of stars. Sometimes, the fragmentation of a comet can even alter its orbit. As pieces drift apart, the distribution of mass changes, creating subtle shifts in the gravitational center. Smaller fragments, with less inertia, are more easily deflected by solar radiation pressure, forming fans of dust that spread along the comet's trajectory. Over time, these remnants become meteor streams, intersecting Earth's orbit and producing the showers we see in the night sky. The debris of a broken comet thus continues to interact with our world long after the parent body is gone. In this sense, fragmentation is both an ending and a transformation. A comet's death can seed new wonders, meteor showers, trails of dust, and fine grains that fall through our atmosphere, carrying microscopic clues about the chemistry of the early universe. The cycle continues, creation through dissolution, knowledge through loss. If we step back from the equations for a moment, there's something deeply human in this pattern. Comets remind us that impermanence is not failure. They live by falling apart, revealing through their endings what endurance alone could never show. Each break, each flare, is a confession of their nature that to exist under light is to change. This understanding also changes the way we look at 3I Atlas. If, in the coming months, it shows irregular brightening, if its structure shifts or fades unexpectedly, it may not signal anything exotic or unprecedented. It might simply be doing what comets do when warmed by a new sun, releasing, cracking, yielding. Perhaps, in that yielding, it tells us of its long journey, of the frozen winds of another star, of the fractures born not yesterday but eons ago. Astronomers will watch closely. Polarimetric data will reveal the alignment of dust grains. Photometry will track brightness fluctuations. Spectroscopy will search for changes in gas composition. Each measurement will add to the story of stress and response, of matter under transformation. Through these observations, we can reconstruct the hidden forces that lead to the moment of breaking. And beyond the science, there's something strangely comforting in this, that even in the vast silence of space, the same principle holds true as on Earth. That all things fragile can be understood not by their permanence, but by how they fall apart. The story of fragmentation, however, is not only about internal stress. It is also about environment. The sun's influence extends far beyond heat and light. It sends out streams of charged particles, the solar wind that sculpt and reshape cometary material in ways both subtle and profound. When fragments interact with this wind, their ion tails respond like delicate threads, aligning and bending. It is there, in the meeting of dust and plasma, that the next chapter of our journey begins, a chapter not about breaking, but about the dialogue between comets and the living breath of the sun itself. When a comet approaches the sun, it enters not only a region of heat and light, but also one of invisible winds and magnetic whispers. Space, though we often imagine it as silent and still, is filled with motion, charged particles streaming outward from the sun in a constant gale. This is the solar wind, a river of plasma that flows through the solar system, carrying with it the sun's magnetic field, fluctuating, turbulent, and alive. And when that wind meets the fragile exhalations of a comet, the result is one of the most beautiful and instructive interactions in nature. You see, a comet's tail is not a single structure, though it may appear that way to the eye. It is two worlds entwined: the dust tail, which curves gently away from the sun, and the ion tail, which stretches straight and true, a luminous thread drawn taut by magnetic forces. Each responds to different masters. The dust tail follows the slow push of sunlight, each photon imparting momentum to tiny grains, bending their path into a graceful arc. The ion tail, on the other hand, is ruled by the solar wind. Charged molecules from the comet's coma are caught in this flow and carried outward at immense speeds, aligning themselves with the magnetic field lines embedded within the plasma. This is why the ion tail always points directly away from the sun, no matter where the comet is moving. It is not an extension of the comet's trajectory, but the consequence of its surrender, the comet yielding part of itself to the wind, allowing its material to be swept into the grand currents of the heliosphere. To look at a comet, then, is to watch a dialogue between two forces, the outward breath of the sun and the inward gravity that tries, however faintly, to hold the comet together. The sun's influence extends far beyond warmth. Its wind varies in density, speed, and magnetism, shaped by solar cycles that wax and wane over years. When a burst of energetic particles erupts from a solar flare or coronal mass ejection, the wind intensifies. If a comet happens to be in its path, the ion tail reacts instantly, twisting, flickering, sometimes breaking apart in sudden, ghostly waves. Astronomers have long used these events as natural laboratories for plasma physics. The tails become indicators of space weather, mapping the invisible structure of the interplanetary magnetic field. From Earth, or from spacecraft, we can trace these effects in exquisite detail. A kink in a tail may reveal the passage of a magnetic discontinuity, a shift in the orientation of the solar field. A sudden brightening might indicate an increase in ionization as higher energy particles strike the gas molecules. In this way, comets serve as living sensors, their delicate structures recording the state of the solar environment as they pass through it. And yet, despite these dramatic responses, comets themselves are too small to disturb the sun in return. The balance of scale is overwhelming. The sun's mass is so great that even the largest comets are mere dust motes in its breath. When a sungrazer, a comet that passes within a few solar radii, dives toward the blazing corona, it is vaporized almost instantly. For a time, astronomers once wondered whether such close encounters might trigger solar activity, perhaps by injecting material into the sun's outer atmosphere. But observations, refined by decades of data, show that the effect is negligible. The sun's storms are born of its own magnetic heart, not of passing visitors. Still, these encounters hold value beyond their physical impact. They are moments of intimacy between worlds, the final gestures of a body giving itself entirely to light. The sight of a sun-grazing comet, captured by solar observatories, is haunting. A small, brilliant streak approaching the sun's limb, glowing fiercely for a moment before disappearing forever. It is annihilation as revelation. In that brief flare, we witness the unity of forces, gravity, radiation, magnetism, all converging on a single point of transformation. For comets farther away, the solar wind's influence is gentler but more enduring. Over days and weeks, it sculpts the tails, shapes the emission of ions, and interacts with the comet's magnetic environment. Every active comet generates a miniature magnetosphere, a bubble where the flow of charged particles is slowed and deflected. This interaction region, known as the cometary ionosphere, forms through a process called charge exchange, where solar wind protons steal electrons from the comet's neutral gas. The resulting ions are swept downstream, creating the luminous blue glow that trails the nucleus. If we could ride alongside such a comet, we would see not a tranquil scene but a constant storm. The solar wind would roar past at hundreds of kilometers per second, carrying ripples and eddies in the magnetic field. The boundary of the comet's induced magnetosphere would shimmer and shift, pulsing in rhythm with the flow. Within it, waves of plasma would propagate, oscillating as new ions are created and accelerated away. It is a symphony of interaction, complex, chaotic, and utterly beautiful. Spacecraft have given us glimpses of this realm. Missions like Giotto, Rosetta, and others have crossed the invisible shock fronts surrounding comets, recording sudden changes in magnetic field strength and particle energy. These measurements reveal how comets carve cavities in the solar wind, deflecting and slowing the plasma flow. The scale of these cavities depends on the comet's activity. A more vigorous outgassing produces a larger, more pronounced region of interaction. In essence, each comet becomes a transient, moving laboratory for studying how plasma and neutral gases coexist. There's an almost poetic symmetry here. The sun breathes out, the comet breathes back. The solar wind strips ions from the comet's surface, and the comet in turn enriches the wind with new particles: water, carbon monoxide, nitrogen, dust. Each exchange is a conversation across distance, a mingling of materials that binds the solar system together. Every particle released by a comet becomes part of the heliospheric medium, drifting outward until it is swept into the broader interstellar flow. And that raises a fascinating point. The boundary between the solar wind and the interstellar medium, the outermost edge of the sun's influence, is itself shaped by this constant interplay. The material ejected by comets, planets, and solar flares all contribute to the pressure and composition of that vast frontier. In this way, comets, though small, participate in the cosmic dialogue that defines the shape of our solar home. Sometimes, though, these interactions can mislead us. A sudden change in a comet's ion tail may coincide with a solar flare, leading to speculation that the comet triggered the event. But correlation is not causation. To disentangle the two, scientists examine timing, direction, and independent solar indicators, radio bursts, X-ray emissions, magnetic field data. In almost every case, the timing shows that the flare occurred first, its effects reaching the comet minutes or hours later. The sun remains sovereign, its tempests self-born. Still, the pattern of coincidence tells its own story. It reminds us how intertwined everything is. A disturbance on the Sun can echo across hundreds of millions of kilometers, reaching a fragile comet and reshaping its tail within hours. Light takes minutes to make the journey. Charged particles take longer, but their arrival is just as transformative. To watch a comet's tail respond is to witness the reach of the Sun's power, the way its presence defines every corner of its domain. As we study these processes, we find ourselves not only understanding comets but the Sun itself. Each interaction reveals how magnetic fields twist and reconnect, how plasma behaves under changing conditions, how energy moves through the medium that fills our cosmic neighborhood. In this sense, comets are not mere visitors but collaborators, silent witnesses helping us map the invisible forces that sustain our world. And there is something deeply moving about that idea. These small, transient bodies, born from the coldest regions of space, teach us about the very heart of the system they visit. They are emissaries from beyond, yet they illuminate the nature of our own star. Their fragility becomes a lens for understanding strength, their fleeting existence, a guide to the enduring rhythms of solar power. In the coming years, as new instruments peer more deeply into the interaction between the solar wind and cometary material, we will learn to read these patterns with even greater clarity. Perhaps, one day, we will follow these lessons beyond our solar system to the winds of other stars, to the behavior of exocomets under alien suns. The principles remain the same: plasma, magnetism, motion, and light, all woven together in a cosmic dance. And yet, for all the grandeur of these interactions, there remains one question that continues to stir imagination and caution alike. What if one day, among the signals we detect from these visitors, the radio echoes, the optical pulses, the spectral lines, we find something that doesn't fit, something that feels deliberate? Not the chaos of plasma or the signature of ice, but a pattern too ordered to ignore. It is in this boundary between curiosity and speculation that our next inquiry begins, where science meets the whisper of the extraordinary, the question of signals, of meaning, of whether the universe is speaking in ways we have yet to recognize. When the thought first arises that perhaps a signal or pattern we detect from the sky might not be entirely natural, it brings with it a strange silence, a pause that stretches between excitement and disbelief. For as long as we have looked upward, we have wondered whether the universe could ever answer back. Every telescope, every receiver, every deep space probe is built not only to observe, but, in some quiet way, to listen. Yet the act of listening brings responsibility, because the line between a natural anomaly and an artificial signature is finer than we imagine. And if history has taught us anything, it is that the cosmos is far more inventive than we are. The search for extraterrestrial intelligence, what we call SETI, is, at its heart, an extension of that same curiosity that drives us to study comets and stars. It is not born of fantasy, but of logic. The universe is vast, filled with billions of galaxies, each containing countless suns. To assume that life arose only here, on one small planet orbiting one unremarkable star, feels improbable in the extreme. And so we listen, scanning the sky for signs that intelligence, like light, may have spread across space. But how would we know if we found such a signal? What would it look like? SETI scientists often focus on a narrow range of frequencies, where nature is quietest regions of the radio spectrum, between the natural emissions of hydrogen and hydroxyl, around 1.42 GHz. This is the so-called hydrogen line, a frequency that hydrogen atoms, the most abundant form of matter in the universe, naturally emit. It is also, perhaps not coincidentally, a universal marker that any technologically advanced species might recognize. In this silent band, a narrow, repeating tone would stand out sharply, against the cosmic background. There are other methods too, optical SETI, for instance, searches for laser pulses, flashes of coherent light that could travel vast distances without distortion. Some programs analyze the time structure of signals, looking for sequences that repeat with a precision unlikely to arise from natural processes. The principle is simple. The universe is noisy but disordered. Intelligence, by contrast, often leaves the fingerprint of intention, regularity, symmetry, rhythm. Yet, as tempting as it is to leap from the strange to the sentient, experience demands caution. The universe has fooled us before. Pulsars, when first discovered in the 1960s, emitted radio pulses so regular that they were briefly nicknamed LGM for little green men. It turned out they were rapidly rotating neutron stars, their beams sweeping across Earth like the lighthouse of a dying sun. What had seemed like the mark of intelligence was, in truth, the song of physics played on a collapsed star. The same discipline applies today. If a comet's behavior or a signal near its path seems unusual, the first question must always be, what natural mechanisms could produce this? Could it be reflection of solar radiation, modulation by plasma, interference from terrestrial sources? In an age when radio transmissions fill the air around our planet, the challenge is not hearing signals, it is filtering them. Earth itself is the loudest transmitter in the solar system, a constant storm of data leaking into space. To help separate speculation from evidence, scientists use frameworks like the Rio scale and the San Marino scale systems, designed to assess the significance of potential extraterrestrial signals. The Rio scale, for example, considers factors such as the credibility of the detection, the distance to the source, and the potential implications of the finding. A simple, unexplained signal rates low. A confirmed, repeatable transmission from a specific celestial location rates high. This structured approach ensures that even our dreams are held to the rigor of data. The essential rule is reproducibility. Any detection that might hint at intelligence must be observed by multiple independent instruments, ideally from different parts of the world. A signal that cannot be repeated, that appears once and never again, is a ghost, interesting, but not proof. Many such ghosts have appeared over the years. Mysterious blips, narrowband tones, transient bursts. Some fade into statistical noise, others are traced to satellites or distant quasars. None, so far, have passed every test. And yet, we keep listening, because the act of listening itself is a declaration of hope that reason and curiosity are enough to bridge the void. Suppose, just for a moment, that a signal were found near an object like 3i Atlas. How should we respond? The temptation would be immediate speculation, a messenger from beyond, a technological artifact disguised as a comet. But responsible science moves more slowly. The first step would be verification, confirming that the signal is real, not a product of instrumentation. The second would be localization, determining its precise origin. Is it truly associated with the comet, or merely a coincidence of direction? The third would be replication, observing it again, ideally by independent teams. Only after all this could discussion begin about its nature. SETI protocols also emphasize transparency. Any potential detection must be shared openly with the international scientific community. There can be no secrecy, no private announcements. The goal is to prevent misunderstanding, to allow for collective analysis. In a connected world, misinformation travels faster than light, and a single premature claim could spiral into chaos. So the process is careful by design, deliberate, patient, almost ritualistic. It might seem, at first, like this caution robs discovery of its magic. But in truth, it does the opposite. For if ever such a signal is confirmed, we will know that it has survived every challenge, every test, every doubt. It will be the most profound finding in human history, and it will be trusted precisely because we doubted it first. There is also an ethical dimension. How we interpret and announce a discovery of potential intelligence reveals as much about us as about the cosmos. Do we approach it with humility, recognizing that we are newcomers in an ancient universe? Or with fear, projecting our own instincts for conquest onto what we do not yet understand? Even the act of deciding whether to reply, whether to send a message back, demands reflection. It is not just a scientific choice, but a philosophical one. Over the decades, many have argued that humanity should remain silent, listening but not transmitting, lest we reveal ourselves to unknown powers. Others believe that silence is a form of arrogance, that communication, even at the cost of vulnerability, is part of what it means to be conscious. Perhaps, as Carl Sagan once suggested, any civilization advanced enough to cross the stars would also be wise enough to understand. But then again, wisdom is not guaranteed by age or distance. It is a hope, not a certainty. This tension between curiosity and caution defines our relationship with the unknown, and it echoes, in a way, the broader theme of this entire exploration, the balance between wonder and skepticism. The same balance that guides us when we interpret the behavior of a comet also guides us when we weigh the possibility of intelligence beyond Earth. The discipline of evidence is not the enemy of imagination. It is what gives imagination meaning. And so, in the age of digital instruments and global networks, SETI continues quietly, scanning millions of stars, recording petabytes of data, searching for order amid chaos. Machine learning algorithms sift through radio noise, flagging anomalies. Optical telescopes hunt for nanosecond flashes. Infrared detectors monitor the sky for waste heat that might hint at massive technologies, structures that trap starlight or harvest energy. None of these searches have yet found proof, but they have mapped the silence with extraordinary precision, and even that silence, as one astronomer once said, is data. Every null result refines our understanding. It tells us where life is not, or where it may be but cannot yet be seen. It constrains probabilities, sharpening the Drake equation that attempts to estimate the number of communicating civilizations in the galaxy. Each unanswered call makes the next question clearer. In that sense, the search for intelligence is not about contact, but about perspective. It forces us to look at ourselves as part of a continuum, a young civilization learning to listen with instruments that double as mirrors. What we hear, or fail to hear, teaches us about our own patience, our humility, our faith in reason. If ever a signal does come, it will not arrive like a revelation, but like a puzzle. It will begin as a faint pattern in the noise, a set of numbers or frequencies that demand verification. And perhaps, for days or weeks, it will seem uncertain, an echo that may or may not be real. In that uncertainty lies both the thrill and the terror of discovery. Because if the universe is truly speaking, it is speaking in a language we will have to learn. But before that day, we must perfect the art of discernment, of distinguishing natural signals from imagined ones, plasma from purpose. And that art is built not on speculation, but on collaboration, transparency, and patience. For only by moving carefully through the realm of the extraordinary can we hope to reach truth without distorting it. And yet, even with all this caution, one cannot help but feel the pull of wonder. When we gaze at a faint interstellar traveler, like 3I Atlas, and imagine that, somewhere in its cold dust, there might be a story written by more than chemistry. It is not folly, it is hope. Science, after all, is hope made methodical. Perhaps that is the deeper reason we keep listening, because whether or not the cosmos ever speaks in our direction, the act of listening changes us. It reminds us that we are participants in something larger, that the space between stars is not emptiness, but possibility, and that, perhaps, is the truest gift of this search, not the discovery of others, but the rediscovery of ourselves. Still, hope alone is not enough. In a world where information moves faster than understanding, how we share these discoveries, how we communicate uncertainty, risk, and wonder becomes as vital as the discoveries themselves. The challenge of truth in the age of speculation, of maintaining clarity amid noise, awaits us next. For even as we look to the stars for answers, we must learn how to speak wisely here on Earth, where stories about the cosmos shape not only our understanding, but our collective imagination. In every age of discovery, there comes a moment when the science itself is no longer the challenge when the data are clear. The method's sound, but the story we tell about it becomes the real test. The way we communicate what we find, what we think we might have found, and what we simply do not yet know, shapes how the world understands not only the universe, but the very nature of truth. In that sense, the frontier of astronomy today is not only out there among the stars, it is also here, in how we speak about them. When the news of an unusual celestial event breaks a mysterious object like 3I Atlas, a strange signal, a comet fragmenting unexpectedly, it enters a vast ecosystem of interpretation. Scientists see data, the public sees wonder. Between those two visions lies the fragile bridge of communication, and on that bridge, words carry extraordinary weight. A single metaphor, a single adjective, can tip a story from caution to spectacle. Possibly artificial becomes alien craft. Unexplained acceleration becomes proof of technology. What begins as a measurement can transform, within hours, into mythology. It's not malice that drives this transformation, it's the human desire for meaning. The cosmos is immense and indifferent, and we long to see ourselves reflected in it. Every strange phenomenon becomes an invitation to imagine, and imagination, while beautiful, is also volatile. That is why the responsibility of scientific communication is so immense. It is not just about accuracy, it is about proportion, giving mystery its due, but not letting it consume the truth. The difference between vigilance and sensationalism often lies in pacing. Science is slow by necessity. It takes time to check, to compare, to test. The media, on the other hand, thrives on immediacy. The collision of those tempos creates tension. When astronomers release preliminary findings, they do so with caveats, margins of error, probabilities, uncertainties. But those phrases, so vital to the scientific process, rarely survive translation into headlines. Ambiguity becomes certainty, possibility becomes drama, and the delicate relationship between evidence and interpretation is lost. Perhaps this is why we need to think of science communication not as dissemination, but as stewardship. Each discovery is a living thing, fragile, still forming. To release it into the world too soon, or without context, is to risk distorting its meaning before it has even matured. The role of scientists, then, is not only to discover, but to nurture understanding, to build patience into the way knowledge unfolds. History gives us sobering examples. When the first interstellar visitor, Oumuamua, was discovered, its peculiar acceleration led to a storm of speculation. Some suggested exotic explanations before the ordinary ones were fully explored. Within days, the conversation had drifted from physics to philosophy. The public imagination leapt ahead of the data. Yet, when further observations pointed toward a natural explanation, a fragment of nitrogen ice, perhaps, or outgassing too faint to detect, the story had already solidified in popular culture as something extraordinary. The correction never travelled as far as the claim. That imbalance between intrigue and resolution is one of the recurring challenges of our age. There is, however, a deeper question beneath it. How should society handle the communication of low probability, high impact risks, what Blaise Pascal might have called cosmic wagers? If the stakes are vast, should we act or announce before we are sure? Should we alert the world to a possible but unconfirmed danger, or a possible but unconfirmed discovery? The answer depends on how we define responsibility. In the realm of planetary defense, for example, a false alarm about an asteroid impact could cause unnecessary panic, but a delayed warning could cost lives. The balance between vigilance and fear becomes an ethical equation. The same applies, in a quieter way, to scientific claims of unprecedented phenomena. Pascal's logic that rational beings should weigh not only probability, but consequence applies perfectly to cosmic communication. To ignore the extraordinary entirely is to risk complacency. To sensationalize it is to risk discrediting the very tools we use to understand. Somewhere between denial and exaggeration lies a path of reason, where uncertainty is acknowledged, quantified, and shared with humility. That, in many ways, is the modern form of scientific courage, to admit what we do not know without turning it into spectacle. Peer review plays a crucial role in maintaining that courage. The process may appear slow, even bureaucratic, but it exists for a profound reason. It is the scientific equivalent of a braking system, the mechanism that prevents acceleration into error. When data are submitted for review, they are not dismissed or delayed. They are tested against the collective scrutiny of others who know the same language of evidence. Each critique, each revision, is a kind of dialogue between curiosity and caution. The goal is not to dampen discovery, but to ensure that what emerges into public view can withstand the pressure of scrutiny. You could think of peer review as a planetary atmosphere. It filters out harmful radiation errors, biases, premature conclusions, while allowing the light of genuine insight to pass through. Without it, science would burn too hot, too fast. With it, knowledge cools and condenses into clarity. And yet, communication does not end at publication. Once findings are released, they enter the global conversation, and here, the social dimension of science becomes vital. Scientists today must learn to navigate not only data but narrative, not only uncertainty but perception. A press release, a tweet, a quote can shape how millions perceive a discovery. That responsibility is both a burden and a privilege. It's tempting, at times, for communicators to lean into drama, believing that enthusiasm justifies embellishment. But the truth is, the universe is already dramatic enough. The task is not to amplify its mystery, but to translate it. The most powerful stories are those that convey wonder without distortion, that show how uncertainty itself is a kind of beauty. Because in science, uncertainty is not failure. It is the space in which discovery lives. We must also be aware of how narratives of risk shape our sense of proportion. In the public imagination, even a tiny chance of catastrophe can loom larger than statistical reality. Astronomers often confront this when discussing near-Earth objects. A rock passing millions of kilometers away can generate headlines that sound apocalyptic. The key is to convey scale, not to diminish concern, but to place it within the broader context of probability. This same principle applies to events like 3I Atlas. The goal is not to make them seem ordinary, but to remind ourselves that extraordinary does not always mean supernatural. Science thrives on the rare and the anomalous. But the beauty of anomaly lies in what it reveals about the normal, not in how it escapes it. Perhaps then, the real art of scientific communication is empathy, the ability to meet curiosity where it lives without exploiting it. When people ask questions like, "Could it be alien?" or "Is this dangerous?" they are not being naive. They are expressing the oldest human impulse to connect, to prepare, to understand. The job of science is to answer that impulse with clarity, not condescension. To explain, again and again, that awe and evidence can coexist. If the universe is a great conversation, then communication is our contribution to it. And like all good conversations, it requires listening as much as speaking. Scientists must listen to how their words are heard, not just how they are spoken. The public must learn to listen for the difference between possibility and proof. And communicators, journalists, educators, creators must act as translators, preserving the fidelity of both languages. There is also a cultural aspect to this dialogue. Each society, each era, filters scientific discovery through its own values and fears. In the 20th century, the atomic age made every cosmic event a metaphor for power. In the 21st, the age of algorithms makes every anomaly a potential signal. To communicate science effectively now means acknowledging those cultural lenses, understanding that facts do not exist in a vacuum, but in a web of meaning shaped by trust. And trust, once lost, is slow to rebuild. That is why transparency, repetition, and humility matter so deeply. When a discovery is uncertain, say so. When it changes, explain why. People do not lose faith because the truth evolves. They lose faith because they were told it would not. The universe is dynamic, our understanding of it must be too. Perhaps the greatest act of communication, then, is to model curiosity itself. To show that scientists are not oracles, but explorers. That uncertainty is not weakness, but honesty. When communicated with openness, science becomes not a collection of answers, but a shared way of asking questions. And that, I suppose, is what makes the present moment, this era of interstellar discovery and instantaneous communication, both thrilling and perilous. We have the tools to connect the entire world with a single image of a comet or a whisper of a signal. But we must also cultivate the discipline to frame those moments wisely, to slow the story down long enough for truth to keep pace with wonder. As we look toward the future of observation, toward a world of open data, citizen science, and collaboration across continents, the art of communication will only grow more essential. The cosmos is speaking in countless voices: photons, particles, fields, fragments of rock and ice. To hear them clearly, we will need not only better instruments, but better listeners. And so, from the language of communication, we turn next to the architecture of participation, to the networks, the open databases, and the shared curiosity that will define the next chapter of discovery in this unfolding story of 3I Atlas and the human quest to understand what passes briefly through our sky and what it leaves behind. In the age we now inhabit, discovery no longer belongs to the few. The boundaries that once separated professional astronomers from the rest of humanity have begun to dissolve, replaced by a web of shared data, open observatories, and collective curiosity. The sky, for the first time in human history, is becoming a place of participation. Anyone with an internet connection can peer into the archives of space, trace the motion of a comet, or even contribute to the detection of something new. It is a quiet revolution not driven by technology alone, but by the human desire to be part of the story of the cosmos. You see, science has always been collaborative, but never before has it been this distributed, this democratic. Large telescopes still scan the heavens, but their raw data flows freely through networks that connect continents. Amateur astronomers, people watching from rooftops, deserts, or frozen valleys, can now contribute observations precise enough to refine orbital models, detect faint variations, or confirm transient events. When 3I Atlas was first noticed, the cascade of follow-up data did not come only from institutions. It came from individuals, from small observatories and backyard setups, equipped with modern sensors and guided by the same spirit that drove Galileo to lift his telescope 4 centuries ago. This is what we call citizen science, the meeting point of curiosity and accessibility. It has turned the sky into a shared canvas, where thousands of eyes work together to paint the most detailed picture of the universe we've ever known. The beauty of it lies not only in the scale of participation, but in the diversity of perspective. A researcher in Chile may collect high-resolution spectra, while an enthusiast in Poland tracks brightness variations through a simple photometer, and someone in India contributes timing data that refines the trajectory. Each observation, small on its own, becomes part of a larger pattern, a networked intelligence, a collective instrument stretching across the planet. The open data movement amplifies this spirit. Space agencies and observatories have learned that knowledge grows by being shared, not guarded. Missions like Gaia, TESS, and the James Webb Space Telescope release enormous datasets into public archives, allowing anyone professional or not to explore the same material from which discoveries are made. This democratization of access transforms science into something participatory, not performative. It invites us all to join in the act of looking up. There is something profoundly moving about that. It means that discovery is no longer a distant spectacle delivered through press releases or documentaries. It can be experienced directly, at home, by anyone who cares to look. In a sense, the universe has never been closer. And yet, this closeness demands something of us, a kind of digital literacy of the cosmos, an understanding not just of how to access data, but how to interpret it with care. The challenge, you see, is not the abundance of information, but its meaning. Terabytes of raw observations stream from telescopes every night, each one filled with potential anomalies, faint trails, unclassified sources. To find significance within that sea requires both human intuition and machine precision. Artificial intelligence now assists in this process. Algorithms trained to spot outliers, to recognize the subtle signatures of transient phenomena that might otherwise escape human notice. But even as machines grow more capable, they rely on us for context. A computer can flag the unusual. Only a mind aware of history and physics can decide what that unusual means. This collaboration between human and machine mirrors the collaboration between scientist and citizen. The boundaries blur. Data that once required supercomputers can now be processed on laptops. Discoveries that once took institutions now emerge from collective networks. We are building, without quite realizing it, a kind of planetary observatory, decentralized, self-sustaining, and profoundly human. And it's not just the tools that have changed. The philosophy has too. Open science is not merely about sharing data, it's about sharing the process of discovery, itself, the uncertainties, the iterations, the incomplete steps that precede understanding. When a dataset is released openly, it invites reinterpretation. Mistakes are caught sooner, insights emerge faster. The act of collaboration becomes a safeguard against isolation, against the narrowness of a single perspective. This is especially vital in moments of ambiguity, when something unexpected appears in the sky, when an anomaly challenges our models. In such cases, the transparency of data becomes the foundation of trust. When anyone can examine the same observations, check the same measurements, and reproduce the same results, the conversation remains grounded in reality, not rumor. It is a collective defense against the distortion of wonder. And yet, there is poetry in this openness too. Imagine people across the world, from children with backyard telescopes to data scientists in observatories, all focused on the same faint speck moving across the night, a comet from another star, perhaps, or the lingering light of a dying sun. The act of shared observation becomes a form of unity, a reminder that we inhabit the same small world under the same vast sky. Technology has made this unity tangible. Platforms now allow real-time coordination between observers on opposite hemispheres, creating continuous coverage of transient events. Automated telescopes respond to alerts from space missions, pivoting within seconds to capture fleeting phenomena. The global network behaves like a single organism, its vision uninterrupted, its attention vast. It is as though humanity has grown a new sense, a collective eye, always watching, always learning. But with that new sense comes new responsibility. Open data can empower, but it can also mislead if misunderstood. Algorithms can reveal patterns, but they can also amplify bias if not designed with care. The democratization of science must be matched by the democratization of understanding education that teaches, not just how to use information, but how to question it. The integrity of discovery depends not on access alone, but on the cultivation of wisdom. Perhaps that is the next great challenge, to build a culture that values curiosity as much as certainty and collaboration as much as credit. In traditional science, recognition often followed hierarchy, the first author, the principal investigator. But in the new landscape of shared discovery, those hierarchies begin to dissolve. Contributions come from every level, every corner of the world. The reward shifts from ownership to participation, from I found to we saw. This shift has emotional depth as well as intellectual. It transforms discovery into something communal, even spiritual. When someone in a distant village reports a new variable star, and their data helps refine a professional catalogue, they are no longer outsiders to science, they are part of it. The barrier between the watcher and the world being watched grows thinner, and that intimacy changes how we feel about the cosmos. It becomes less a stage for distant forces and more a living context that includes us. The data we collect, every photon, every spectrum, every timestamp, is more than measurement. It is the record of our shared gaze. Each entry in an archive is a moment when someone, somewhere, looked up and cared enough to record what they saw. Over time, these moments accumulate into a collective memory of the universe. In 1,000 years, perhaps, beings not yet born will scroll through these archives and see how humanity once saw the sky. And in that way, open data becomes more than science, it becomes legacy. It also becomes resilience. When knowledge is distributed, it cannot be lost. When data are shared freely across borders, no single failure, political, institutional, or technological, can erase it. Open science ensures that the story of the universe continues. Even if our institutions change, it is an architecture of continuity, built not of stone or steel, but of shared attention. In this light, the story of 3i Atlas is not just a scientific event, it is a case study in collective curiosity. From the moment it was detected, the world watched, measured, debated, collaborated. Images flowed across forums. Orbital models were refined by teams separated by oceans. Theories were tested in public view. The object itself traveled through space in silence, but its passage ignited a global chorus of observation. That is what science, at its best, can be: not competition, but conversation. And perhaps that conversation is leading us somewhere deeper still. As the tools grow more powerful, as the networks expand, we begin to see patterns not just in data, but in ourselves, in how we organize knowledge, how we share truth, how we sustain wonder in an age of automation. The next frontier may not be about building bigger telescopes, but about building stronger connections between disciplines, between people, between ways of seeing. Because as the universe grows more transparent, the question quietly shifts from what is out there to what do we do with what we now know. The cosmos is giving us its data freely, scattering it across the digital ether. The responsibility is ours to listen wisely, to collaborate truthfully, and to act with care. And that, I suppose, leads us to the next horizon, to the question of meaning. For even as we map the movements of interstellar travelers and catalogue the structure of the universe, we cannot escape the deeper wonder. Why do we look at all? Why does the act of seeing the cosmos change how we see ourselves? To follow that question, we must turn inward from data to philosophy, from observation to understanding, into the quiet domain where science and meaning begin to meet.